So if you had a chance to play a bit with the FET site, the animations for electric charge, hopefully that'll give you an idea of some of the numbers that we're going to be dealing with down here. Because electric charge has got a much, much stronger force than gravity does. So it's intriguing that we'll usually talk about thousandth or a millionth of a charge or a billionth of a Coulomb, which charge is measured in that way. Now, there are three ways that they're typically talked about in terms of calculating the number base. Just like when we were talking about forces, we had arrows, and we calculate forces down to newtons. Well, we're going to do the same idea with electric forces. Electric forces or electric fields, the first one here, it's probably the hard thing is saying, which one do I apply when? Which formula am I going to use for? Well, if you don't get any information about a second charge that's in a problem, it's probably going to be this kind of a problem that's up here, where you have to determine what's the field of, if you put a charge in, it's like pre-solving the problem. So once you get your charge, you just plug in the distance and the charge, this will tell you what you multiply by your charge, and it will give you an answer. You don't have to do any more formula work. You just take what your charge is times this answer, and that will get you what the force on that subject is. So it's interesting, but they're really the same. You're going to see it's 9 times 10 to the 9th. When you're looking at this, they all have that same term in here. So it's 9 billion, basically, times a charge, times, in this next case, it's 9 billion times 2 charges. So you can see these are very similar. And if you were not given a charge, you're going to use this first one. Okay, so say, what's the field at 2 meters from a charge? No word about that second charge, so then it's this first equation. If it says, what is the exact charge between two particles, and they give you the distance, which is way more the kind of problems that you face. So most of the time, I think this second law, which is the electric force that one is going to be using. And electric force is a force, so it's got a unit of newtons. All right, so that was when you're done with the problem. We're going to do that. Force is 9 billion, 9 times 10 to the 9th, times the two charges that you're comparing, and divided by the distance squared. It's not too bad of a formula to put those numbers in. Okay. So that will give you the force of push or pull. If they're opposite sides charged, they're going to be pulling together, and if it's the same size, they're going to be pushing apart. And the last thing in terms of charges is, what's the potential energy? Now, if you remember, we talked about forces. If you're pushing a force, or you're lifting something, and you walk a couple of meters, or you lift it up 2 meters, whatever that force was, times the distance that was accomplished with that force, that was energy. And if you remember the last unit we did in Module 1, once you know energy, that really simplified a lot of problems. So the potential energy around a charge, if you want to move a charge from 2 meters apart to 1 meter apart, for instance, that is calculated by still taking your 9, it means force times distance, so it's this formula, force times the distance, and that's going to take one of these distances out. So it looks just like this, but the distance in the bottom of the fraction is gone away. So it's 9 billion times the two charges divided by the distance between those two charges. And if you're moving from one space to the other, remember the change in potential, delta, is the final minus initial. If you remember delta phi, or instead of semper fi or something, whatever rings in your mind, but final minus initial, phi, is always the distance that the direction you're subtracting. So if you have a charge that's 5 meters away and one that's 1 meters away, your final position is 1, minus the initial position is 5. So if these things, what's the change in potential, which usually you give as a delta symbol, then you're going to say, well, what was the change in distance? Delta D. So that's going to come out, maybe I can write that in. So change in, let's see if my change in potential energy is equal to 9 billion times the two charges divided by change in the distance, which is just really final minus initial, okay? So when you're doing those kinds of problems, just look, where was the two changes? You're just going to take the subtraction of those two. That's going to be a simple number, 5 minus 1 or 4 minus 2 or something. That's going to go on the bottom. But these shouldn't be that tough in terms of calculations. It's really knowing which of those formulas goes in. If they don't say anything about the second charge, it's this first formula called the electric field calculation. If they give you two charges and those are the ones that are interacting, then it's the electric force problem. If it says how much does the potential energy change, which we usually call volts in terms of properties here, then that's going to be the just a distance at the bottom. So it's 9 billion times the two charges divided by distance. All right, give those next problems a try. That's all we have for today, and that's going to take you some time to work through those, but good luck.